In this lesson we'll look at the different types of CPU processor architecture. You're going to need to be able to identify the three types of architecture, what are the characteristics of each and how they are similar and how they differ. These are our keywords that you should already know. You need to look back through your notes and check that you can give a clear definition of each of these. This is the last section of 1.1.1, structure and function of the processor. You need to think of computer architecture as the structure and organisation of the actual computer system. Think of the CPU, how it's laid out and how it accesses memory. You need to think of the components that make up a computer system and how they're interconnected, and this is the architecture. In the early days of computer systems, you'd have to perform manual tasks. You'd have to pull out a series of switches and plug them into different locations. This is extremely time consuming and the output would depend on where you put the switches. You can see an example of this as the Colossus machine. It was used by Alan Turing to decode the German Enigma codes. You'd have to set up the different switches every day to try and figure out the different combinations. If you are interested a little bit more in this, there is a really good film to watch called The Imitation Game. One of the main problems of reprogramming is the time constraint that it takes. Think that you have to move every single switch to a different position. It's inefficient. Every time you wanted to produce a new calculation, these switches had to be moved. So we had to start looking at the different theory that might change. The concepts between a memory unit started to change this thinking. This meant that you could store data as well as programs. It was John von Neumann who developed the idea of storing data as a bit. Remember, a bit is a 0 or a 1. And this is what they got the name for his type of architecture. His concept is that all computers should have a processor, a memory unit which uses buses to connect data to memory, connections for I/O, input and output, and secondary storage. Now, his concepts were theoretical, but his theory said that both instructions and data could be loaded into the memory unit at the same time. So that means that you needed a set of addressable locations, which we know as registers. In the main memory, we know that we need to move data by something called buses. And von Neumann architecture is considered to be the basis now for most modern day computers, but be careful with this. Now with computers moving forward, it's hard to recognise a processor as sitting into one concept, as we've included several different concepts into a processor. So this is a theoretical model which is not really used perfectly in practice. This is an abstracted view of the von Neumann concept. You can see the processor and the memory, with the secondary storage sat on the right hand side, and the input and output devices feeding into the processor. There's one set of buses here. We're going to have a look at a different type of architecture called the Harvard architecture, and it's worth comparing those two abstractional models. We are extremely lucky to be living in Manchester because the first computer that was actually created to have stored instructions was developed at Manchester University, and it was called Baby. You can now see this computer at the Museum of Science and Industry, and it's worth you actually going to have a look at that computer. The link on the slide takes you to Manchester University's history and heritage about computer science. Manchester University is one of the leading universities for computer science research and development, as you will see through this link. The next information is just for you to get a flavour of Manchester University's history with computer science and the heritage that we have in the local area. So in 1934 they created the first differential machine in the world. If you do maths or further maths, you'll understand a little bit about differential calculations, and this machine did that for you. As we've looked at already, in 1948 the Baby machine was developed. Look how it was just after the Second World War, after the Colossus machine, so not long, there's not much of a gap between those two. It was invented by two men called Freddie Williams and Tom Kilburn at Manchester University. Now the Baby is clever because it fetches instructions from the memory unit, and then these are executed one after the other. This is done by a processing unit, and it was originally designed to perform simple arithmetic and logical operations. So if you go to view it, you'll be able to see basic binary being inputted, and then you'll be able to see a result in binary. So this means that machines are now more versatile. You can run different programs, different sums and additions into the same computer using this architecture. This is this stored program concept, which has then paved the way for modern day computers, which are general purpose computers, using that von Neumann concept of storing data. The clever thing about the baby machine was it was the first appearance of RAM, random access memory. Remember, this is volatile memory which disappears when you turn the computer off. Now again, this part is not in the specification, but in 1950 Alan Turing actually joined Manchester University. He joined and became Deputy Director of the Computing Machine Laboratory. Now he developed at Manchester University the Turing test, which is still massive in artificial intelligence today. This is a test to decide whether a computer is real or not. In 1964, Manchester University was actually the first university in the UK to develop a computer science degree. And they are one of the top universities now for computer science because of their history and heritage in research and the development of computer science technologies. They currently provide a massive range of degrees. This is an example of a BSc in computer science. They're usually 3 years long, and a typical A-level offer would include 1 A star and 2 A's, with an A star in mathematics. You could potentially get into Manchester University with an AAA, and they do favour computer science as well. This is a range of the different courses that they actually provide. There are a few more on the second slide. There is a big movement in artificial intelligence at the moment, and you can see there are a range of different courses that you could take if that's the route you wanted to take. You can also take computer science with other subjects such as mathematics, and there's lots more different options there. Here are a few more of the different types of degrees that you can do at Manchester University, including software engineering. Remember, this lesson we were looking at processor architecture. Now in 2018, the SpiNNaker project was run at Manchester University. It was completed in 2018, but it has been running for a number of years. Now this machine has 500,000 processors in an architectural design. So it's used for communication between its many processors, and it tries to mimic the way that the human brain works, thinking about neurons in the brains and how they are connected. There is a nice video that you can watch to give you an overview of the SpiNNaker, and that's on the side of this slide. This is an extended learning opportunity for you. If you want to watch a celebration and a series of lectures about SpiNNaker, then some of them are on YouTube, and this is a celebration of 1 million processors. In the USA, they developed the electronic numerical integrator and computer, known as the ENIAC computer. It was the first electronic general purpose digital computer. So building on that kind of work that was done with Baby. There is a different type of architecture that has been developed called the Harvard architecture. This is where instructions and data are held completely separately. You probably find this in a lot of embedded systems and digital signage processing. So I've given you a few examples there: audio, speech, sonar, etc. Now this needs 2 different sets of buses. One set of bus goes to the instructions and moves the instructions between the processor and the instruction memory, and the second set of buses moves data from the data memory unit to the processor. On the right you can see an abstracted view of the Harvard architecture. This time, as you can see, there are 2 parts to the memory: the instructions and the data. So remember, those 2 things are held separately. Now this generally means it's faster than von Neumann, so it's used for systems which need much faster processing. Because they're kept separately, it means that we can actually fetch parallel instructions, so we can be fetching an instruction and the data element. So think of the von Neumann, we're doing one fetch cycle after the other. When we're pipelining, we might be doing a fetch, decode and execute at the same cycle. Well, this one, you can almost be fetching an instruction and fetching data at the same time. So remember the features. It's used in digital signage or embedded systems. Instructions are held separately to data, and that might mean that we can use two separate buses to transfer data to and from the processor and storage. We also use the Harvard architecture in microcontrollers, or it's a similar kind of Harvard-like architecture. And again, we use these in smartphones. But just remember that this is a theoretical model. Actually, in practice, this doesn't happen. There are a combination of different architectures which are developed. Should you want to do any extended research, you can have a look at this link just here. Now, this is a match-up task. However, here are the answers. Let's quickly go through it. The von Neumann architecture is used in most PCs, conventional PCs and laptops that we use. This basically means that any general purpose system would use the von Neumann architecture. That's so it can switch between tasks. That might be running music in the background whilst working on something else. Whereas the Harvard architecture is usually used for things like digital signage, embedded systems, mobile communication, where speed is important. So, for example, a traffic control camera where you need to capture a number plate if somebody's driving too quickly on a road. But it can't switch between different tasks. That's all it can do. Remember, for von Neumann, data and programs share the same memory. There's a disadvantage to this which can be exploited by hackers. Harvard may store some instructions in ROM, whereas malware can be used to exploit the fact that data and programs are saved in the same location. When you're thinking about the Harvard though, you can actually have different sizes and different word lengths, and it can be adapted to the size of the program. So that means that your instruction memory might be different and might be different size to your data memory. So you can actually have a little bit more kind of flexibility there in the size of the memory. For Neumann, you only have one system bus. In Harvard, you have two system buses which can run in parallel. Remember, because you have different data memory and instruction memory. But that means in von Neumann, programs can often be optimized in size, whereas they tend to be large in Harvard. And von Neumann gives that more flexibility so that you can run a variety of programs. You're not likely to know what programs are going to be running. So it gives that flexibility that you can adapt to what programs need to run and what the user needs to run. In theory, most high-performance CPUs use aspects of both the types of processors. Because remember, these are theoretical concepts, they don't generally stick to one. In one design, there is one main memory, remember, for holding data and instructions, but often the CPU cache is also divided into instruction cache and data cache, whereas Harvard architecture is, remember, separate data and instructions. But if you think about it, if you've got a separate cache for data and instructions, well, you are touching on the Harvard architecture there as well. Please answer questions 1, 2 and 3 of the exam questions. You'll find these on Google Classroom. Once you've done that, pause the video and then mark your answers using the exam specification and answers at the end of the exam questions. Then you need to improve your answers with a different coloured pen. In the next lesson, we're going to actually be doing a comprehension style test. It's not exam questions, it's just the key terms and can you actually give me correct definitions of these. Remember, at A-level, it's all about using technical language, being able to show an understanding of the different keywords. So I want you to make a revision resource. You're going to have to submit that revision resource to me, and then next lesson we'll complete a comprehension test.